All right. So now we'll. So far we have seen the definition of statistical thermodynamics. We have seen the difference between thermodynamics and statistical thermodynamics. We have taken one example for a biological system, and we have defined distribution of states, and from there we have defined the thermodynamic probability W. Now, let's look at Boltzmann distribution law, the very important law in statistical thermodynamics, and we'll derive the Boltzmann distribution law. So let's consider an n particle system with total energy capital E. So as I said, the total energy I'll be defining as capital E, and energy for the states will be defining as epsilon. So for the ith state, the energy I'll take as epsilon I. So we have a n particle system with total energy E, and the particles are distributed as follows. So n0 particles in energy level epsilon 0, number of particles in energy level epsilon 1 is n1, number of particles in energy level epsilon 2 is n2, and so on and so forth. So my total number of particles n is sum over n0 plus n1 plus n2 plus all other terms, which we write as sum over I ni. Likewise, our total energy E is sum of n0 epsilon 0 plus n1 epsilon 1 plus n2 epsilon 2, and so on and so forth, which you can write as sum over I ni epsilon I. Okay. Now I need to go here. So as you have seen, thermodynamic probability W is n factorial divided by n0 factorial, n1 factorial, n2 factorial, and so on and so forth. And this we can write as n factorial, which is total number of particles, and this we can write as product over all ni's factorial. So this is my W. So if I take ln of this, we take ln W is equal to ln n factorial minus ln of okay, now this product becomes sum when you take the ln, right? So so we write ln ni factorial. Now we can now since n is large, n is your total number of particles, which is very large, we can apply Stirling's approximations. What is Stirling's approximation? So Stirling's approximation is that ln, this you can write as x ln x minus x. So Stirling is a scientist, and he given this theorem that if x is when x is large, I can write ln x factorial as x ln x minus x. So if we apply that in our expression, we can write ln w is equal to n ln n minus n minus ni ln ni, and then minus minus becomes plus, so sum over ni, which is nothing but n. So this term and this term goes out, and we get ln w is n ln n minus sum over I ni ln ni. Okay. Okay, now I need to go up. Okay, so now, so this W is the thermodynamic probability, and you see you have this W is the thermodynamic probability, and that thermodynamic probability changes all the time since particles are moving up and down. So since particles go up, come down, so as they move up and down, the thermodynamic probability also changes, and thermodynamic probability becomes maximum at equilibrium. So at equilibrium, W or ln W is maximum, and therefore d, if you take the derivative of that, d ln W would be 0. So at equilibrium, W or ln W is maximum, and therefore derivative of ln W is 0. So we can take the derivative of the previous expression where we had d, just so we had d of n ln n minus d of sum over ni ln ni, and thus equal to 0. So now if we simplify the n ln n, so what do you get? So if you take d of n ln n, you get ln n dn plus you get n. So d of ln n is 1 by n dn, so you get ln n dn plus dn, and for the second term, for this term, d of sum over ni ln ni. Likewise, if you simplify, ultimately what you should get is basically sum over ln ni dni plus dn. So if I put them back here, I get ln n dn plus dn minus sum over I ln ni dni dni minus dn, that's equal to 0. So this term goes, and this is again nothing but 0 because your n is constant, total number of particles, and derivative of n is 0. So, this leads us to sum over I ln ni dni is equal to 0. This is a very important expression, but the problem of this expression is we cannot solve this equation any further, and that is because this dni is not independent. Particles are spontaneously and continuously moving up and down, and therefore dni is not independent. So, how to simplify this expression? So, to simplify this expression, we will be calling some important mathematical method proposed by Lagrange, and which is called Lagrange undetermined multiplier. Undetermined multipliers. So, we will be making use of Lagrange undetermined multiplier. So, the expression we got sum over I ln I dni is equal to 0. We will write it down in the next page. Sum over ln ni dni is equal to 0. This is what we got. This is we put expression number 1. So, now since as I said, since dni is not independent, we need to apply Lagrange method. So, according to so following that method, we have to make use of two constant conditions we have. So, we have two constants in our system. So, one constant was total number of particle n is constant. So, therefore, if I write dn as dni is equal to 0, because my total number of particle n is constant, n is fixed, and therefore, derivative of n is 0, and dn is nothing but sum over I dni. This is one constant we had. We also had another constant, which is total energy also has to be fixed. So, if E is the total energy of the system and that is fixed, so we take d of E, and d of E is nothing but d epsilon I dni, and that is equal to 0 because my E is constant. So, these are the two constants we have. So, according to Lagrange multipliers, we multiply these two constants with a constant. After that, if we add those two expressions with our parent equation, then the variables become independent. So, at the moment our dni's are not independent. So, now following the Lagrange multipliers, what we are doing, we are basically multiplying constant 1 by a constant alpha dni, and then adding to this expression, multiplying the second constant with another constant beta, adding those two up in my parent expression 1, and they sum up to 0. So, now according to Lagrange, now dni's become independent. Okay, so we can write this as ln ni plus alpha plus beta epsilon I dni is equal to 0. So now here so now the restraining condition that dni's are not independent is gone. So due to Lagrange multipliers, my dni's are now independent. So that is one, and number two, but this dni, it cannot be 0. dni cannot be 0 because particles are always moving up and down, and therefore dni, which basically talks about change in number of particles across the state, that is non-zero. So applying these two conditions, what we get from this expression is that we write ln ni plus alpha plus beta epsilon I is 0. So we go to next page. So we write ln ni plus alpha plus beta epsilon I is equal to 0. So you got ln ni plus alpha plus beta epsilon I is equal to 0. Now you know that we know n is sum over ni. So okay, from here we can write ni as e to the power minus alpha e to the power minus beta epsilon I, right? So you can write ni as e to the power minus alpha times e to the power minus beta epsilon I. And since we know n is equal to sum over ni, we can make use of this expression here, and if you put this expression here, we get e to the power minus alpha e to the power minus beta epsilon I. Since alpha is a constant, we can write e to the power minus alpha as n divided by sum over e to the power minus beta epsilon I, right? So let's give some name of the number of this expression. So let's say this is equation number A, this is equation number B. So combining A and B, we get ni is equal to n e to the power minus beta epsilon I divided by sum over e to the power minus beta epsilon I. This is the famous Boltzmann distribution law. So what this distribution law says? This law says that number of particle in the state with energy epsilon I is ni. So ni is number of particles having energy epsilon I at equilibrium. So Boltzmann distribution basically dictates the distribution of particles across the energy states. Okay.